we're talking about linear ones, okay? So after the midterm, this is almost all of the cases that we have been discussing. We have been talking about second order linear differential equations in different cases, if they are homogeneous, non-homogeneous, and so if I want to complete this big picture for you, I must say that, okay, when we are talking about second order linear differential equations, we talk about homogeneous equations and non-homogeneous equations. The general form of a second order homogeneous equation is something like this. Pxy prime plus qxy equal to 0. Here p of x and q of x are functions of x alone. And if you have the same equation, but this time, instead of having it equal to 0, if you have it equal to a non-zero function of x, then this is called a non-homogeneous differential equation of second order, which is linear. Okay? So, what was the solutions of homogeneous equation? Solutions. In the general form, if you remember, we said that our y of x, which we normally show it by y(g) of x c1, c2, because it is also going to come with two constants. How was the general form of it? It was a linear combination of two linearly independent solutions y1 and y2. We can only write this equality if y1 and y2 are linearly independent. And the key for checking if two solutions of this differential equation, if they are independent or not, was very simple. Either we divide these two functions to each other. If it is a constant, then they are linearly dependent. But if it is a function of x, or it is not a constant, then they are linearly independent. Another way was to calculate the non-skin of y1 and y2, which we defined as non-skin of y1 and y2 as this determinant y1, y1 prime, y2, y2 prime. And we have shown that this is going to be a function of x, and it is going to be non-zero in the domain that is going to be defined. And on that domain that it is not equal to 0, then these two functions coming from the solutions are going to be linearly independent. Okay? So it is the nature of Wronski. Either it is equal to the constant function 0, or it is completely not equal to 0. Anyhow, this is just a reminder, but we can keep it anyhow. What about solutions of non-homogeneous equations? If you remember, we said that if we want to solve non-homogeneous differential equations, we need to first make them into a homogeneous equation. How? We assume the reduced equation, which means that if you have this non-homogeneous equation, just assume that right-hand side is equal to 0. So it is in this homogeneous case. Solve it, find these two linearly independent solutions. Then the solutions of this is going to come as this general solution, C1, C2, plus a particular solution. Okay? Or in general, it is going to be C1, Y1 plus C2, Y2 plus Y of x. And as you see, this is not coming with any constant C1 or C2 or whatsoever. This is particular solution. And this is called the general solution of the equation. Okay. few cases that we need to consider. But let's start from here, talking about the non-homogeneous cases. Build up the picture, and I will again come back to these non-homogeneous cases and talk about the finding ways of we use to find that particular solution. Okay. So what we have here, and we need to follow, is that if we are given a homogeneous equation, okay, what are the ways to find this y1 and y2? What is our steps? What is the first step? Guess two solutions and check. This is always our first attempt in solving a second-order differential equation. We look at the equation and we try to some kind of conjure up or come up with the solutions. And if we can come up with these two solutions, the thing that we need to do is just only check if they are really solutions, which means that take the first derivative, second derivative, and plug it into the equation. If the equality is satisfied, then those two are solutions of our equation. Then we need to check for linear independency. And if you have been able to guess two linearly independent functions, we write the general solution as this. Okay? What happens if we cannot guess two solutions, but we only have one solution? Guess one. Then what would happen if you call it y1? Yes. You're right, we are going to use this one in order to find another solution. Guess one and use it to find another. How do we do this? Here our y2 of x is going to be v of x times y1 of x. And our v of x, if you remember, was defined as integral of 1 over first solution to the power of 2 e to the power of minus integral of px, dx, dx. And this px is the coefficient of y prime when we are having the normal form of homogeneous equation, which means that the coefficient of phi double prime is equal to 1. Okay? Let me jump here above. Okay. So if you have been able to find two solutions, good. What about if you have been able to find only one solution? It is again good. You just use this formula in order to find the second solution. You have had many of this kind of exercises in your homework exercises. Anyhow, but what about we have none of the two solutions? We are not able to. Not characteristic, you're going one step further. We need to check for special equations. Check for special equations. What was our special equations? First one of them, yes, equation with constant coefficients. Equation with constant coefficients. What was the general form of this equation with constant coefficients? Yes.
Plus p y prime q y.
Yes. And since we are talking with homogeneous equations, it is fine. So if we have this type of an equation such that here p and q are just fixed real numbers, in order to find two linearly independent solutions of this equation, what we need to do is to generate this characteristic equation and find the roots. Okay? How did we come up to this characteristic equation. Again, we are using this guessing and checking thing. We have guessed that maybe y equal to e to the power of mx is going to give us a solution. Because our intuition was this. If I'm taking derivatives of e to the power of mx, the first one or second one or whatsoever, I'm still dealing with the same type of function. So, the same type of functions with different coefficients can only come up and be equal to 0. So this is a valid assumption. And we have come to that point and we have seen that yes, it's actually working. So what was our solutions if we had the roots of this equation? What was happening then?
P squared plus minus.
We have either two real solutions or two real roots for this equation which are distinct, m1 and m2. So if I have two real roots, m1 and m2, come back and replug it here. So our y1 is going to be e to the power of m1x, our y2 is going to be e to the power of m2x. And you can check that they are linearly dependent. Then you can write the general solution as c1 e to the power of m1x plus c2 e to the power of m2x. Okay? What if we have one repeated root which is real? Then what will happen? Here we will have m1 equal to m2, right? The two roots. So we can guess one solution, which is going to be e to the power of that m1x. And for finding the second solution, you need to use this one. I have one solution, I need to find another second one. How do we do? If you plug these things, you will see that our v of x, for the equation with constant coefficients, it is always going to be equal to x. So our second linearly independent solution is going to be x e to the power of e m1x. And then you can write their linear combination and have the general solution. What about if we have complex conjugate roots? A plus IB, A minus IB. Let's say this m1 is A plus IB, m2 is m minus IB. Then we have this form which we also see exponentials and also trigonometric functions. So it is going to be e to the power of ax cosine of bx, one solution, e to the power of ax sine of bx, another solution. They are linearly independent, we just need to write the general formula as it is. After equations with constant coefficients, what is our second type of special equation that we know how to solve and grab these two solutions? Yes, it is Euler's or Cauchy's equation. Equidimensional equation, but anyhow. What was the general form of Euler's equation? Please.
X power of 2
Yes.
multiplied by I prime and
I double prime.
I double prime
Yes.
plus
Pxy prime.
I prime and Qi.
Yes. Qy equal to 0. Here again, P and Q are real numbers, fixed real numbers. How did we solve this equation? Again, we looked for the characteristic equation, right? And how was the characteristic equation? Here we assume that this was our point. We have a function. I need to again use this guess and check method, right? It is all that I have in order to start digging and trying to find what's happening. You see, I have an x multiplied by my derivative of the function. I have x to the power of 2 multiplied by our second derivative of the function. But we need this whole thing to be equal to 0. This only happens when we are taking derivative and multiplying with x, or taking the second time derivative and multiplying by x to the power of 2. Then the type of equation, the type of solution is not changing, the type of function. And for which cases this can happen, we have said that, okay, maybe it is going to work for x to the power of m. See, because second time derivative, this is m minus 2. With this multiplied with it is going to come back to x to the power of n. This is x to the power of n minus 1 with some coefficients. X is multiplied, this is come back to x to the power of m, again x to the power of m. So a combination of them is equal to 0 if their coefficient, that coefficient that is appearing must be equal to 0. That coefficient, we call it a what? Characteristic equation again. But this time the characteristic equation for this was what? m2 plus p minus 1m plus q equal to 0. Okay, characteristic equation. Again, it is the same. Again, what was our stories? When we had two real different or distinct roots for this equation, what was the general form of our solutions? I calculate the roots of this. I have two really different roots, m1 and m2. What is my test function? X to the power of m, right? I just need to plug that m1 and m2 here. X to the power of m1, x to the power of m2. These are two valid candidates for the solutions. There are actually solutions, and if you check, they are going to be linearly independent. Since they are linearly independent, we can write the general solution as c1 x to the power of m1 plus c2 x to the power of m2, for the case of Euler's equation. What happens if you have two real roots which are repeated? Then what happens? Then I can only guess one of these solutions, right? X to the power of m1 or x to the power of m2. How can I guess or find out the second solution? Definitely I'm going to use this one. Okay? And here, if you remember, we calculated this v of x for the Euler-Cauchy equation, and it turned out to be ln of x. So our first solution when we have real repeated roots or a real double root, then we have that, this is x to the power of m1, and the second solution is going to be x to the power of m1 multiplied by ln of x. Okay? What about if we have complex roots? Again, m1 is equal to a plus ib, m2 is equal to a minus ib. Then what will happen? Again, we are placing that a plus ib here instead of m, but opening the expressions. So it is going to be x to the power of a cosine of parentheses b ln of x. This is one solution. And another solution is x to the power of a sine of b ln of x. So that is the whole case. What will happen after this? What will happen is that we will have general functions, general equations, such that these general polynomials as their coefficients, f2 of x y prime plus f3 of x y equal to 0. Okay? Such that fi's are polynomials or power series. In this case that we are going to talk about towards the end of today, we use power series. Today we will talk about this. And actually power series solutions will be some kind of continuation of this kind of trying to figure out what kind of equations to do. Okay. This is a picture about homogeneous equations. So when you are solving a problem or when you are dealing with something, you need to open this map up, okay? And this is the continuation of this column. And try to figure out where you are in this picture. Because based on that, you can use the solutions and methods that we are developing and discussing in order to solve your problems, okay? But the problem is this. You see how we are trying to organize this material in such a way that, okay, it is clear how we are starting, where we are going. This is the important thing that you need to keep learning, to learn about how to learn things, okay? Anyhow, let's come back to the non-homogeneous case. If I am allowed to be a little bit doing something like this. Okay. In order to find particular solutions of an equation with constant coefficients, let me start from here. I have this one. And I want to find solutions for equation with constant coefficients such that it is not a homogeneous equation. How can I find this kind of solutions, yp? We have discussed about two things. Today we are going to talk about the third one of them as well. The first thing that we do in order to find yp was what?
Is it the sine or cos function or e to the power of function or the program?
It was under one of the methods, which was called the method of undetermined coefficients, right? Undetermined coefficients. And when did we use this? When our right hand side was an exponential or a sine or a cosine or a polynomial. Okay? What was our second method that we used? Variation of parameters. Yes, definitely. Variation of parameters. And when did we use this? When y1 and y2 are available. If y1 and y2 are available, you can also use this for the general case as well. But when our equation is an equation with constant coefficients, we know already what is y1 and y2, and we can immediately try to write that formulas and figure it out. I have no place to review them. Also, I need to just drive them because I haven't memorized all of that formulas. But yeah, you know what is the case. The third one that we're going to talk about today is the operator methods. Operator methods. Okay. Variation of parameters was developed by Lagrange, a mathematician. Operator methods are also developed by another mathematician, Heaviside. You will see, when we are trying to look at something as an operator, it is going to become a little bit strange for you. Heaviside also had the same objections when he was trying to develop these operator methods, but they are actually useful, and they will give us a hint towards how can we generalize our methodology that we have been trying to deal with to higher order linear differential equations with constant coefficients. We will cover them today and we will talk about them, okay? I need to give you two more things before talking about operator methods and talking about power series solutions, but if you want, please take a photo of the board so I can clean it someplace at a time. Let's see if reduction of order, especially in our second textbook, Martin Brown's book. If you look at it, he's saying that, okay, this is actually a reduction of order, because if you do this assumption, plug them in the equation, then over there you're actually solving a first order differential equation. So we are some kind of reducing this second order differential equation into a first order differential equation. That is why they're calling this method a method of reduction of order. But in our main textbook, we are not using this for this term. We are saying that this is just finding one solution based on another solution. Okay? And reduction of order happens in the following cases. Reduction of order. And how can it help us? Reduction of order helps us in order to, if we have, for instance, a second order ODE which is not linear, okay? Maybe it can help us try to tackle it and turn it into a problem that we know how to solve it. That is why it is also useful and we need to have an eye over it. When we are talking about reduction of order, which is something similar to this, but not totally, we are talking about reducing our differential equation to a non-differential equation. How this happens? In two cases. Let me just. Yes, when we are doing reduction of order, we need to have two cases in order to be able to do this. First of all, when our equation is looking like this, which means that there is no dependent variable. Dependent. What will happen in this case? We can just take y prime as a new variable. Let's call it v. What will happen to our second derivative if we take this? It is going to be v prime. By these assumptions, what is going to happen to our general equation? It is going to be, I'm just replacing everything, it is going to be x, v, v prime equal to 0. And if you look at this, this is a first order differential equation. And we know how to solve them. Okay, for instance, x y double prime minus y equal to I need to have this y prime as well, okay? You are given this kind of a differential equation. How do you solve it? Let's discuss about it. First of all, we need to try to understand if this is a linear equation or a non-linear equation. Or we need to understand if this is a homogeneous or non-homogeneous equation. Or, yes, the first question that we normally ask ourselves is about the order of this differential equation, right? It is a second order differential equation. After having a second order differential equation, then we are having a different map to look for it. In this map, is it a homogeneous, is it a linear equation or not? It is linear, right? You see, you have some function multiplied by the second derivative, minus some function multiplied by the first derivative, plus 0 multiplied by the y, equal to something. So it is in the general form of the general schema of linear equations. Good. Is this a homogeneous or non-homogeneous equation? This is a non-homogeneous equation. So what kind of solutions are we going to get? We are going to get solutions from our reduced homogeneous equation, x y double prime minus y prime equal to 0. And we are going to get two solutions, y1 and y2. And we are going to calculate a particular solution because this is a non-homogeneous equation. You can use those three methods. Today, but we are going to talk about operator methods. Keep that in mind. Okay. Now we know that this is non-homogeneous and we need to find the particular solution. In order to start dealing with this, we assume that it is a reduced equation, and now we are dealing with the homogeneous linear second-order differential equations. How can we solve this? Can you guess two solutions for it? Maybe it is hard. Can we guess only one solution for it? It is also maybe a little bit hard. Okay, so what is the next step? The next step is to look to see if we have these special cases of equations or not. Is this a differential equation with constant coefficients? No, because we have x's here. Pass. Is it an earlier equation or not? Why not? Yes, definitely. If I multiply this with x, then this is going to be x to the power of y double prime minus xy prime plus 0y equal to something like so this is actually an Euler equation. As an exercise, please try to solve this Euler equation, okay, by yourselves. What if we have checked and we have seen that, okay, it is still not working. It is not an Euler equation. What should I do? I should try to look for this reduction of order. I'm just trying to see, is there any y appearing in the equation or not? Do we have any y's? No, we do not have. So we can reduce the order, which means that we can turn this second order differential equation into a first order differential equation. If this is my v, if this is my v prime, I just need to replace them, right? So what do I have? I have x v prime minus v equal to 3x to the power of 2. Look at this. What do I have here? 1 over x v equal to 3x. What is this? A first order linear non-homogeneous equation. How did we solve first order differential equations? This is a linear first order differential equation, right? We had to multiply this with something that we have already obtained it from integrated factors, if you remember. We need to multiply both hand sides of this equation with that e to the power of minus integral of p of x here, which is minus 1 over x, if I'm not wrong. In order to turn this into derivative of multiplication of two functions, just take the integrals and do the rest. So I'm leaving it as an exercise for you. The second case for our reduction of order will happen when our equation does not have the independent variable or no x's are appearing, which is going to be looking something like this. No independent variable. What will happen then? Again, we are taking y prime equal to v. This is actually dy over dx. What is my y double prime? It is going to be derivative of v with respect to x. But I'm just going to write this chain rule form, dy over dx, okay? And what do I have? What is our dy over dx? Dy over dx is the y prime, or it is equal to v. So instead of this, I'm just writing v. So it is going to be v in this case, my equation turns into an equation with y v dv over dy equal to 0. Again, I am able to reduce it into a first order differential equation. This time our variables are v and y. An example. How can we solve this differential equation? First of all, a question. If you want to tackle this equation, what should you do? What is our steps? What is the procedure? Or how should we systematically look at how we can solve this differential equation? Is this a second order equation or first order equation? Good. So the next step, is it a linear differential equation or not? Second order linear or not? It is a linear second order differential equation. Okay. Homogeneous, non-homogeneous? Homogeneous. Since it is homogeneous, we know that the solutions are going to be C1y1 plus C2y2 and no particular solution. Good. Can you guess two solutions for this? Maybe not. Can you guess one solution for it? Maybe not. No problem. That is the whole point of developing these systems and this, because we are not going to be able to guess the solutions because they are going to be super complicated. So I don't know about this, the second one and the first one or whatsoever. So what is the next steps? Try to look at the equations that we know how to solve. And what are the steps for that equation that we know how to solve? First is the equation with constant coefficients. Is this an equation with constant coefficients or not? What is the coefficient of y double prime? 1, just a constant. Here, let me also write that this k is just a real number. What is the coefficient of y prime? 0, again a constant. What is the coefficient of y? K to the power of 2, yes. Again another constant. So this is a differential equation with constant coefficients, right? You know how to solve it. How do we solve this? We need to write the characteristic equation for equation with constant coefficients. And it is m to the power of 2 plus 0m plus k to the power of 2 equal to 0. From here, what is our roots? m1 is equal to ik, m2 is equal to minus ik. So in this case, our a is equal to 0, b is equal to k. So what are we going to have? E to the power of 0x times cosine of bx or cosine of kx. So cosine of kx is one solution. Another solution is e to the power of 0x sine of bx, which is going to be e to the power of 0x 1 times sine of kx. And this is going to be the second solution. Okay? So we know that this is actually, we have also talked about this. This is the equation for the harmonic motion. Okay? So that is why we have solutions of sine of kx and cosine of kx. But anyhow, how can we solve this equation using this method that we have here? We already know what are the solutions. Very good. But how can we reduce the order and try to figure these two out? What we have done here, just trying to replace them. If we replace them, what do we have? Instead of y double prime, I need to write v dv over dy plus k to the power of 2y equal to 0. Can I write this as v dv plus k k to the power of 2 y dy equal to 0. Is this a first order differential equation or not? It is, right? We have seen many of these forms. Is this differential equation separable or not? It is already separated. We have v dv, we have k to the power of 2 some number, y dy. So I just can integrate and have the solution. So it is going to be v2 to the power of 2 divided by 2 plus k2y2 equal to some number. I'm just going to use a trick here. This is going to be apparent after a few steps. I'm just multiplying both hand sides with 2, and instead of this 2c0, I'm just going to write, let me v to the power of 2 plus k2y, k2y2, k2y2 equal to, I'm just going to write k to the power of 2, a to the power of 2. And a is another constant. Okay? Here you can figure out what is a. That 2c0, make it equal to this, and from here you can get it out. What now? My v is going to be equal to my v, which is dy over dx. This is equal to plus minus k square root of a to the power of 2 minus y2. And if you look at this differential equation, this is also another separable differential equation, which I can write it as dy divided by a2 minus y2 plus minus k dx. From here, if I take the integral, and if you remember this integral, it is going to be arc sine of y divided by a, and here is going to be plus minus k x plus c. So what can we write for our y? Our y is going to be a times sine of plus minus kx plus c, which you have seen before that we can write this in this form. C0 sine of kx plus c1 cosine of kx. Okay? Again, we are having the same solutions that we had found. Is it clear what's happening? Good? If you want, take a picture of the board, and we can also have 10 minutes of break, then we can continue. Okay. We have been talking about non-homogeneous equations in two cases for finding the particular solutions. The first method was the method of undetermined coefficients, such that we have an equation with constant coefficients. It has some right-hand side which is not equal to 0, which makes this equation a non-homogeneous equation. If we want to find particular solutions, in order to write that general solution, c1y1 plus c2y2 plus yp, if our right-hand side is a function of exponentials or sine or cosines or a polynomial, then what we can do is that, okay, for each one of these types, select a corresponding function with undetermined coefficients, plug it in the equation, write it down, and we will figure out what is going to happen with that coefficients, so we can find the particular solution. The second approach was that if I have a non-homogeneous differential equation. And I have two solutions for it. It doesn't really matter for the equation to be with constant coefficients in the method of variation of parameters. If that is our case, then we need to find that V1 and V2 that we have talked about them. We were using Wronski's and we have used Kramer's method to find out that formulas. Then from here, we can find Yp as Y1 V1 plus Y2 V2. And then we are done. Our third approach is that we are going to use operator methods in order to solve this kind of non-homogeneous equation. The beauty of this method is that it some kind of turns everything into a process of integration. If in this integrating process, if we suppress constants of integrations, then we are going to get only the particular solution. If we do not suppress this constant of integrations, then we are also generating the general solution as well for the homogeneous equation. You will have it as an exercise, but that is the whole case of it. So what is the essence of the operator method? And when we are talking this operator method, what we are really talking about? The thing is that, let's assume that we are symbolically behaving with this derivative. What do I mean by that? Whenever we are writing d over dx of some function, right? This is interpreted as derivative of y, right? Instead of this, I'm just going to symbolically write dy, or should I write it in this way? Okay? So whenever I see a d in front of a function, which means that we are just taking its derivative. Okay? What about d2 of a function? How do we define it? We define it as the second derivative of this function y. What about d to the power of n y? Again, it is going to be the nth derivative of the function. Okay? Now, taking this symbolically, how can we write this equation in these terms? In the terms of these? Instead of y double prime, what should I write? D to the power of 2 of y. What about this? P d of y. P times derivative of y, right? Plus q times y equal to f of x. Can I write this in this form? D to the power of 2 plus pd plus q. This derivative applied to this function equal to f of x. Can we give this some meaning to this? I'm taking a factor out of this y, but you see, if you just replug it here, then this is going to be d over dx. D to the power of 2 over dx to the power of 2. So this is something meaningless. It seems something super meaningless here, right? But symbolically, when we are behaving with this operator, look what you see. Is this something similar or familiar to you or not? Is this representing our characteristic equation or not? So what is this? This is also a polynomial in the operator d, right? How can we give a meaning to this? Because if I can give a meaning to this, some derivative operator operated on y gives me f of x. Symbolically, if I want to find this y, what can I write? I can write this as 1 over e to the power of 2 plus pd plus q of f of x. Okay? We assume that this is not a derivative operator. Assume that this is just some constant, like it is a polynomial. If I want to find out y, what should I do? I should divide both hand sides, right? But what is the meaning of this thing? Is this something meaningful? Or how can we make sense of this? You see, this is, if you look at it and if you replace what we have here, it seems a completely stupid thing, right? What happens to have this derivating operator without having any functions or whatsoever? But this is also going to help us in order to understand functions in a different way. An operator actually here, what you see, an operator is itself again a function, but another type of function. It gets a function and plugs out another function. Let me write some examples for that. What is our d of x to the power of 2? Just come back, use the definition. What is this going to be? D over dx of x to the power of 2, right? And what is this going to be? 2x. D of x to the power of 2 is equal to 2x. Something else. D of sine of x. What is d of sine of x? If this d is the derivative operator, cosine of x. Let me show this something like this. Sine of x equal to cosine of x. What do you see? Can we look at d as a function such that its input is also a function, its output is also a function? What is our impression about functions? Functions are things such that receive numbers, do something, and put out some numbers, right? We are some kind of trying to generalize our notion and our understanding of the function as well. When we are talking about operators, operators are again themselves functions, but this time, instead of receiving a number, plugging in a number and getting out a number, this time we are plugging in a function and we are getting out a function. Okay? This is the whole case about this. We need to look at the functions in a different way, or we need to extend the meaning of the function. Okay. So, if you are looking at this as a valid operator or as a function, how can we give meaning to this now? Because if I'm able to give meaning to something like this, then I'm able to solve this second order differential equation, which is linear and which is with constant coefficients. Let's start from here. If our dy is equal to f of x, then what I'm writing is this, right? I'm writing y as 1 over d of f of x. How can I give a meaning to this? Let's look at the picture from a different point of view. What is the meaning of this? This is y prime equal to f of x, right? If I want to write y, how can I write this? How I can turn this into a y? By integrating, right? So this is going to be integral f of x dx. So do you see any valid candidate for this definition? If I want to define the operator 1 divided by d, how can I define it based on our symbolic manipulation of this stuff? Is it okay for me to define 1 over d of any function as integral of that function? It makes total sense because in this case they're going to be both the same thing. So this is our first thing. d to the power of 2, d to the power of 3, or higher powers of this operator? If I want to write 1 over d to the power of 2, d to the power of 3, and so on, how can I do this? It seems it is going to be turned into taking integral inside integral inside integral inside integral, right? Can we really give something meaningful for this in such a way that we can extend it to this kind of equations or not? Because you see what I'm trying to do? I'm just trying to do this. If I have this d2 plus pd plus q, okay, this is an operator, right? The operator itself, because since I haven't yet plugged any function in it, this is just the operator itself. Can I write this operator as multiplication of two linear forms Because if I can do this, then what I'm doing, I'm actually taking derivative first, then taking derivative again, and I'm arriving at this equation. And if this is true, do they really R2 B minus R? Can I have this commutative property? Because if they can commute with each other, I can some kind of expand these and write it as what? What is our B minus R1, B minus R2 when applied for a function y? This is an operator. This is another operator. This operator is being operated on this function. The result is another function. That is being fed to this operator. So let's try to calculate what is happening if we have this kind of factorizing into its multiplicative forms. So what is this going to be? This is going to be d minus r1. And this is going to be dy minus r2y. Okay? Then what is this going to be? This is going to be d2y minus r2 dy minus r1 dy minus r1 r2y. What can I write here? I can write this here as d2 minus r1 plus r2 d minus r1 r2 of y. Look at this, what is happening. If my r1 and r2, if it is my minus p, if this minus r1 r2, I think it is going to be positive r1 right? Minus r1 minus r2, so it is a positive. And this r1 r2, if this is equal to q, then what I have been able to do, I have been able to write this operator in terms of first order operators. It is a little bit confusing, right? Don't worry, just bear with me. What I'm trying to do is this. I'm trying to give meaning for this kind of an operation. If I have d2 plus pd plus q, and if I have this inverse operator, 1 divided by this, how can I give a meaning to this? For this general case, I have no idea how to give a meaning for it. But I know how to start. I know what is the meaning of 1 over d of f of x. I'm trying to look for cases such that I can extend the meaning of this. If my equation is with constant coefficients, if it is with constant coefficients, I can write that equation here, if you multiply it with y, I can write that equation as multiplication or combination of two operators. And this is true. I'm just going to give it as an exercise to you. If we have an equation with constant coefficients, when our equation is not with constant coefficients, these are not going to change the places. Okay, so they do not commute. Okay, and since they do not commute, it is not going to give us an easy way to, okay, first do this or first do that. It is going to be a precedence and it is going to be a little bit hard for us. But in the case that our equation is with constant coefficients, if we factor our operator into its first degree components, then we can change the order of taking this derivative operator, so we can have an easier working cases. What do I mean by that? Keeping this in mind that we can actually turn this or higher order things into equation with these forms or operator in these forms, I need to just ask for this question. How can I give a meaning for 1 over d minus some number? So let's start from here. D minus r1. How do we define this? We define this as dy minus ry, right? Which is going to be equal to y prime minus ry. If this is equal to f of x, a function or whatsoever, this is equal to f of x. How can I define 1 over d minus r of f of x? Because if I know how I'm going to calculate 1 divided by d minus some number, and if I have this kind of an operator, I can also break it down into this linear components, and I can do what I'm intended to do. Okay? So how can we give a meaning for this? Again, we need to solve that differential equation and try to find it out, right? Look at this equation. From here, what is our y prime? If we want to solve y prime minus ry, r is a constant, equal to f of x. How do we solve this differential equation? If you remember, it is a linear, first order non-homogeneous equation. I need to make this, or multiply it with something, such that I can make this into the derivative of multiplication of two functions. And here my choice is e to the power of minus rx. We have talked about this in the first order differential equations, you will remember it. It is going to be y prime e to the power of minus rx minus r e to the power of minus rx y equal to e to the power of minus rx f of x. What is this equal to? Isn't this equal to y e to the power of minus rx's derivative? The left hand side.
Yes.
Derivative of first one multiplied by the second one plus derivative of second one, which is minus r e to the power of minus rx times the first one, equal to e to the power of minus rx. From here, what is my y? I need to take the integral of both hand sides and multiply it with e to the power of rx. So what is going to be my y? My y here is going to be e to the power of rx integral of f of x e to the power of minus rx dx. Okay? Here again I'm suppressing the constant of integration because I have this integral plus c, which is completely multiplied by e to the power of rx. I'm suppressing it. If I do not suppress that, or do not assume that that constant of integration is plus c, it is not equal to 0. If I have that c, then this is going to be multiplied by that, right? So I'm going to have a particular solution plus c times e to the power of rx. This rx, this r, it is actually coming from the roots of this equation. But you will figure it out in some of the exercises. It is better to write it down and have it. Okay? With this assumption, what is going to be my second definition? So how can I write d minus r of f of x? The aim was to define this, right? So I can define this as e to the power of rx integral of f of x e to the power of minus rx dx. This is going to be our case. Take a picture of the board so I can take the example. Assume that we have the second order differential equation e to the power of minus x, let's call it, okay? And we want to find the particular solution of this differential equation. How can we do it? We have three methods. First is the method of undetermined coefficients. And since it is in the form of e to the power of ax, we can select our particular solution as capital A times e to the power of this ax, and a is here minus 1. Replace it in the equation and try to see what is happening and go on. Or, if we have two solutions of this differential equation, in the homogeneous case, the reduced differential equation, which we already have, because this is an equation with constant coefficients, we can find out two solutions, so we have y1 and y2. We can also use the method of variation of parameters in order to find the particular solution. But our case is going to be like this. If I'm using operator method, how can I find the particular solution? Okay? First of all, let's write this in the operator form. What is going to be? E to the power of 2y minus 3 dy plus 2y equal to e to the power of minus x. So what is this equal to? This is d2 minus 3d plus 2y equal to e to the power of minus x. Okay? I do not know how to make the inverse of this operator, but I know that if I break it into linear terms, I can use 1 over d minus that number or whatsoever. If you look at this as a polynomial, okay? So this is going to be generally like this, right? You have a polynomial in D, which is being operated on y, and it is going to be equal to f of x, right? We need to see that how we can write y as 1 over this polynomial in D times f of x. This is what we are trying to do, okay? But let's come back here. If we take this as a polynomial, can we break it down into its linear factors?
Yes.
What is that?
D minus 2
Times?
D minus 1.
D minus 2 times D minus 1. We can also write D minus 1, D minus 2, or reverse their places, right? D minus 2, D minus 1. Which one of them is the true version? Since our equation is with constant coefficients, we have shown that in this case that the constants are coefficients, you can change the places of these two operators. So it really doesn't matter. And since it really doesn't matter, we can write as we like it. Should I write D minus 2, D minus 1, or D minus 1, D minus 2? Which one would you like to have?
2 to
2, 2. D minus 2, D minus 1, y e to the power of minus x. Okay? From here, what is our y? Our y is going to be 1 divided by d minus 2, d minus 1, e to the power of minus x. What is this? I can actually write this down as 1 over d minus 2 applied to 1 over d minus 1 e to the power of minus x. This is an operator operating on this function. The result is going to be another function. So this is a function. This function is going to be put into this operator, and again the result will be a function. And that final function is going to be our particular solution. If we suppress the constants of integration, let's see. Let's go step by step. What is my 1 divided by d minus 1 e to the power of minus x? I'm keeping d minus 2 here. What do I have? Look at the definition. How did we define this operator? As this, right? So what I'm going to write here, what is my r here? 1. So it is going to be e to the power of x times integral of, what is my function? E to the power of minus x. Okay. What is e to the power of minus rx? E to the power of minus x, right? R is equal to 1. Dx. And what is this going to be equal to? E minus 2 of, what is this? Integral of e to the power of minus 2x. And what is the integral of e to the power of minus 2x? Minus 1 divided by 2 e to the power of minus 2x. It is going to be multiplied with this e to the power of x. So what do we have? We have minus 1 over 2 of e to the power of minus 2x multiplied by ex. So it is going to be e to the power of minus x. Okay? I can write a constant of integration here, but I'm not writing it because I'm looking for a particular solution. But in case that I'm writing it, what is going to happen? Here, I need to write it here. Not here exactly. For this integral, if I want to write a c. Okay, it is going to be c times e to the power of ex as well, right? We will have this one plus c times e to the power of x. Keep that c e to the power of x in mind. Now we have this operator. How do we make that work? Again, we need to use this definition, right? What is 1 divided by d minus 2 operator doing? It is doing something like this. It is e to the power of 2x multiplied by integral of our function, which is minus 1 over 2 e to the power of minus x multiplied by minus 2x dx. And what is this going to be equal to? I think this is going to be right, which is going to be equal to 1 over 6 e to the power of minus x. Okay? Are you sure about this? This is going to be our particular solution. I think we have made some mistake over on the way, right? Because 1 over 6 e to the power 9. No, it's fine. Right? It's fine. This is our particular solution. If we were writing this constant of integrations when we were taking integrals, then we were going to have a c to the power of x plus a c2 e to the power of 2x, which is going to give us the general solutions of this differential equation plus this particular solution when we are suppressing our constant of integration. Okay? The thing is this. Side, partial fraction decomposition. When we are having an operator like this, d minus r1, d minus r2, up to d minus rn, which is going to be applied to some function y. If doing it one by one, step by step, we can also do this kind of a decomposition, which is known as the Heaviside partial fraction decomposition. And it is looking like this. d minus r1, r2, d minus rn, an. As in the method of integrating functions, right? We were separating that fractions into its partial fractions and then we were taking integrals. It is again the same thing. If you have this kind of a complex operator or complicated operator, and let's not talk about complex, it has some different meaning. If you have something complicated like this, we can also break it down into its components, and then what will happen is that we are going to just operate this, plus operate this, plus operate this, plus operate this. So it's going to be from multiplication turn it into an addition. Anyhow, this is almost all of the things that we will be using, but you will also have some other exercises and you will try to also find out what's happening. So, do you have any questions up to now? We are just taking them as symbols, we are symbolically behaving with them, and we are trying to give some meaning to the symbols based on what we know from what we have been developing. Okay, when we are dealing with this kind of operators, you see that we can easily extend our methodology not only to second order differential equations, the equation that have the second derivative, but we can also increase that amount of operators and go to higher order differential equations. So this gives us some idea about how we can deal with higher order differential equations, higher order ODEs with constant coefficients. If we want to talk about higher order ordinary differential equations, which are linear and with constant coefficients they are appearing, then how can we develop a general solution or a general schema? Or how can we talk about this kind of equations? Can we use our methodology that we have developed so far in order to extend it directly into this kind of equations? The answer turns out to be yes, actually. So let's start with the general form of a nth order linear differential equation with constant coefficients. How can I write such an equation? I'm just going to have the nth derivative of y plus a1 right to the power of n minus 1 to n minus 1 y prime plus a n y equal to. Here I can keep this 0, so it is going to be a homogeneous equation, or I can keep it as r of x or whatsoever that you would like. When it is non-homogeneous, then we are in need of a particular solution again. The method of undetermined coefficients or operator methods work here in order to find the particular solution for the non-homogeneous differential equation. But what happens for the general solutions of this homogeneous equation? We can show that the general solution, which we show it by this, and since we have the nth derivative, it is going to include n constants, and we write it as c1, c2 up to cn. This is going to be c1 y1 plus c2 y2 plus up to cn yn. Okay? Which means that if we are having n solutions which are linearly independent, then we are going to have our general solution as this. Okay? But how can we define the linear independence of more than two functions? Is it possible to calculate the Wronskian? Actually, we are able to extend the definition of Wronskian and so on. But when we have n functions, then our Wronskian is going to be the determinant of an n by n matrix, which is super problematic to deal with. Also, we do not have two functions to divide them by each other and try to see if it is constant or not. So what we need to do is that we need to go back to the original definition of linear independency from linear algebra. If that a linear combination is equal to 0, then all of the coefficients must be 0. But I'm not just going to get over there. Just keep in mind that we need to have n linearly independent solution. But what is happening here? How can I find this y1, y2, yn if I'm having this equation with constant coefficients? Again, as our test case, we take this function e to the power of mx, plug it in the equation, and what we are going to get is that we are going to get an equation like this, plus a1 m to the power of n minus 1 up to m plus an equal to 0. Characteristic equation. And we find its roots. Find the roots of characteristic equation, and we will have cases. So we are talking about higher order differential equations that have constant coefficients. For this kind of equations, if you want to solve them, we need to just find out the roots of the corresponding characteristic equation and find the roots. We know how to solve the second degree polynomial equations, right? If I give you a second degree polynomial equation, you will use that delta method and find the roots. What about a third degree polynomial? Do you know the general solutions for the third order polynomial equation? If you have an equation like ax3 plus bx2 plus cx plus d equals 0. Here everything gets a little bit complicated because we need to transform this equation into another kind of equation. Then we need to use Cardano's formula and so on. So we normally don't talk about the general roots of this kind of equation. And I think Abel has proved that the fifth degree polynomial equation does not have any general closed form solutions in terms of radicals. And based on works of Evarist-Galois, we also know that it is impossible for fifth degree or higher equations to write their solutions in terms of radicals and plus minus these coefficients and this kind of things. So there is no general way in order to find the roots of this kind of higher order polynomial equations. Okay? What we need to do is just try to have some smart tricks about finding the roots of this kind of polynomials. But anyhow, normally in your questions that you're going to deal with it, you will have these cases that you will check, okay, for instance, if I place 1, then it is going to be satisfied in this equation. So 1 is one of the roots. I can divide everything by x minus 1 and then reduce the order and do this kind of things. But yeah, it is a little bit easier. Anyhow, but if you are able to find the roots, the following scenarios will happen. If R1, R2, up to Rn are n distinct real roots, then our general solution, which comes with n constants, it is going to be like c1 e to the power of r1x plus c2 e to the power of r2x up to cn e to the power of rnx. Can you prove that e to the power of r1x, e to the power of r2x, e to the power of rnx is n exponential functions such that all of these are distinct and different, are linearly independent? If we can show this, then we can be sure that the general solution is going to be like this. So as an exercise, you can do it. I think we have also discussed it with, not with your session, I think. But anyhow, they are linearly independent. The second case that may happen is that we have this R1, R2, up to Rk are real roots with multiplicity k, which means that this number R1 is going to be a root k times, or when we are just writing that linear factors, it is x minus this R1, but to the power of k, the whole thing. In the general solution, we need to replace the part related to R1 up to Rk by, what I'm saying is this. I'm just having one of the roots repeated for k times. And since I'm just going to make it easier to write, I'm saying that assume that the first k1 of them, they are the same roots. So instead of writing them separately, in this part that we see that k terms, instead of that, write c1 plus xc2 plus, or it says c2x. c2 x to the power of 2 up to ck x to the power of k minus 1 e to the power of r1 x. Okay? If you're having repeated roots, instead of writing them separately, for each one of that repetition, just multiply the solution with an x. And continue this up until you have done it k times, which will end up with x to the power of k minus 1, and then just replace it. What happens if we have, if a plus minus ib is a root with multiplicity k? Then what will happen? If you are finding these complex conjugate pairs and they are appearing k times, again, the place that is related to these, instead of that part, we're just going to write this. E to the power of ax multiplied by c0, let's call it a0. a0 plus a1x up to ak x to the power of k minus 1 multiplied with cosine of bx plus b0 plus b1x up to bk x to the power of k minus 1 sine of bx. And by this, we can reproduce all of the solutions of this homogeneous nth order differential equation. Okay? Can you please solve this differential equation? What do we need to ask first of all? What was our first question when we were dealing with any type of differential equation? We were talking always about, ask about what is the order. Who told us order? Order kim söyledi? Yaradın mı ya? Our first question is always to ask about the order of the differential equation. What kind of an order does this equation have? It has some higher order. So what is the order of this differential equation? It is fourth order. How higher order equations are possible for us to solve? they're possible for us to solve in the case, as of now, and in this course actually, if they have constant coefficients. Is this a higher order or first order differential equation with constant coefficients or not? Yes, it is. It is a linear one. So what do we need to do is just to write the characteristic equation and find the roots, and based on those things try to write the general solution. So what is the characteristic equation of this? M to the power of 4 minus 5 times m to the power of 2 plus 4 equal to 0. Can you please find the roots of this fourth degree polynomial equation?
M square minus 4.
M squared minus 4.
M square minus 1.
M squared
Minus 4.
minus 4.
And minus 1.
How can I develop this further?
M minus 2 times M plus
M minus 2, M plus 2, M minus 1, M plus 1 equal to 0. So can you please find out the roots and write the general solution? We have 1, minus 1, 2, minus 2. So we just need to have what? We are in this case, right? We have 4 different cases. So our general solution is going to be c1 e to the power of minus x plus c2 e to the power of x plus c3 e to the power of minus 2x c4 e to the power of 2x. Good. Let me give you another example. What about this one? First of all, what is the characteristic equation of this first order linear differential equation, homogeneous linear differential equation with constant coefficients?
Power minus 8 m squared plus 16.
Can you please find the roots? How can we make this simplified? I'm listening to, a few of you simultaneously. That is why I'm getting lost in between what's happening. So maybe if you can speak up, I can focus on one of you and understand what's happening.
Hocam burada her iki eksi2'den 2 tane var. O zaman
Tamam.
biz kökler eşitliğiyle üsttekini beraber kullanabilir miyiz?
Yes, we are going to use this. But first of all, let's first deal with this, find the roots, then come over there, okay? So this is my point that we're trying to make. This is actually this one, but I can also divide this into m minus 2, m plus 2. Okay, so this is going to be m minus 2 to the power of 2, m plus 2 to the power of 2 equal to 0. So what do we have here? Yes, exactly. This is our point. So we have, for instance, R1 equal to R2 equal to 2. Our third root and our fourth root, they're also the same and they're equal to minus 2. So what is happening? We have repeated roots, right? What should we write as our general solution? Our general solution is going to be, I need to write c1 plus c2x or xc2, doesn't matter, c2x multiplied by e to the power of 2x, and here I am replacing c1 e to the power of 2x plus c2 e to the power of 2x part in this general form. They are repeated, so I'm just making them using this, replace it, plus I have this c3, c4, right? But again, since they are repeated roots, I need to replace that c3 and c4 with a form like this, which is going to be looking like c3 plus c c for x e to the power of minus 2x. Good? Okay. Another thing that we need to talk about is that almost up to now, we have never talked about higher degree differential equations. We need to also tuck that into the picture and get rid of it. So, why not? Higher degree first order problems. I'm not going to talk about higher degree equations of higher order. I'm just taking a first order derivative and I'm trying to write an equation which involves higher degrees of this derivative. General form of this is going to be our first derivative to the power of n plus a function of xy multiplied by y prime to the power of n minus 1. Okay? F of n minus 1 of xy y prime plus f of n xy y equal to 0. Can also have get rid of this, yeah. Because y prime to the power of 0, I can also get rid of this. This is the general form of first order nth degree differential equation. Is it a linear differential equation or not? Is it linear or non-linear? It is definitely non-linear because we are having high order terms, right? So y prime and this kind of things are multiplied to each other. So this really have a non-linear nature. If we can factorize the equation above to its following formula. Y prime minus g1 of xy, y prime minus g2 of xy, up to y prime minus g of gn of xy equal to 0. You see, we are just trying to factor it out into its linear terms, and each one of them are turning into a first order differential equation. Then we can solve the followings. What do I have here? I have first of all this equation, y prime equal to g1 of xy. Y prime gn of xy. What do you see here? This is a first order differential equation. We know how to solve it. The second one is as well, the third one as well, up to the nth one. We are having n first order differential equation that we know how to solve them. We have talked half a semester about them. If we solve each one of them, then we are just going to write something, right? X, y, or whatsoever equal to c. Bring all of them into one hand side, maybe the left hand side or right hand side or whatsoever, and call that form that you see as, for instance, psi1 of x, y, and c. So this is the solution of this equation. Okay? Do this for all of them. So psi1 of x, y, c equal to 0 is the solution of this equation. Psi I of x, y, c is the solution for the i's equation, and up to all of them. Okay? We solve all of them separately. Then, let me call this star, then the solution of star are psi1 of x, y, c, psi2 of x, y, c, up to psi n of x, y, c equal to 0. Okay, what do I mean by this? If we have y prime to the power of 2 minus 1 equal to 0. How can we solve this? First of all, is this a first order, second order? What is the order of this differential equation? It is first order. It is first order. What is its degree? It is, yeah, or second degree. But this is a nonlinear first order differential equation. For higher order differential equations, for higher degree differential equations, if we want to solve them, we need to be able to factorize them into their linear parts. Can we do this for this equation? How can we write this equation? As the multiplication of these linear terms. Can I write this as y prime minus 1, y prime plus 1 equal to 0 or not? I can write this, right? So what is going to be my first set of equations? Y prime minus 1 equal to 0, or y prime equal to 1, and y prime plus 1 equal to 0. What are the solutions of these equations? If y prime is equal to 1, what is y equal to? X. But we have a c as well, right? What about here? Minus x plus c. Okay. So what is our, in this case, what is our psi1 of x, y, c equal to? We need to just take all of these to the left hand side, right? So it is going to be y minus x minus c. Okay? What is my psi 2 of x, y, c? It is again y plus x minus c. So my general solutions are going to be what? Y minus x minus c, y plus x minus c equal to 0. Okay? When you solve each one of these differential equations, put them to one hand side, call them that function psi1 or whatever you would like to call, and the general solution is going to be multiplication of these functions equal to 0. Multiplication of all of these equal to 0. Okay? The topic that we are going to discuss, and we will continue next week before coming to the end of the semester and talking about Laplace transforms, is that what is our methodology that we are trying to develop or have the map of this second order differential equations? We have the homogeneous ones, non-homogeneous ones, we talked about them. And in the case of homogeneous equations, we started with guessing two solutions. If it's fine, good. Guessing only one solution and trying to find another solution by the first guess. If you also do that, it is fine. But we have some cases that we are not able to directly guess what is our solutions, y1 and y2. For this, we need to develop a general method that we can answer our questions regarding this differential equation. The simplest case of differential equation that we know how to solve it was a differential equation with constant coefficients, which were looking like this. The next level of equations were actually equations that had this x to the power of 2 px. You see what is happening? From equation with constant coefficients, we came up to the Euler's equation, or Euler-Cauchy equation. And what is happening here actually? You see? Instead of writing fixed real numbers as our coefficients, now we are changing our functions. The simplest case of functions that we ever have is about these polynomials. The next level of equations that we can try to show to us or introduce to ourselves is that if instead of writing this just one term of polynomials, can I add complicated polynomials or not? For instance, can I have equations which are looking like this? You see? This is another polynomialized coefficient. This is another polynomialized coefficient. And this is not in the class of this equation or this equation. If you remember, this is Legendre equation. You have been able to find one of the solutions and then trying to find the second solution as well. For the case that our p was equal to 1 in one of the homework exercises. But we will come to that. What about this kind of an equation? Which is the Bessel's equation. Is this an equation such that its coefficients are polynomials or not? Yes, we have a polynomial x to the power of 2. We have a polynomial x. We have this polynomial x2 minus p2. Can I have other kind of polynomials as well? Can you please tell me one of your favorite polynomials? This is a question that you will never hear again in your life. But if you have any favorite polynomials, can you let me know about it? For instance, x2 plus 1. What is your favorite polynomial? Can you let me know about a polynomial? Tell me a polynomial. Another polynomial maybe, if you would like to have it. Okay. Now, our question is this. If I'm having this kind of differential equations, how can I solve them? Which means that if I'm having this f1x y double prime plus f2x y prime plus f3x y equal to 0, where fi's are polynomials. And as we develop and go on, we will also see that not only it is going to work for polynomials, but we can also say that if these are power series as well, but we will talk about some special points that we need these to be analytical functions and so on. At the end of the lecture, I will give you a summary of power series and analytic functions and this kind of things. But anyhow, if these are not only polynomials but also power series as well, how can we solve them? How can we solve them? So my question brings down us to the question of, again, guessing a type of function y such that if we plug it into this equation, then we are going to be able to cancel these things out in order to come and arrive to 0. So what kind of solutions do we need to have here? Telefonlarımızı, cihazlarımızı bırakırsak çok sevinirim. Yani hepiniz secdeye gitmişsiniz gibi böyle çok hoş bir görsel yok. Tamam mı? If we want to solve this kind of a differential equation such that coefficients are polynomials, what kind of a solution is possible for me to have? For instance, if this is polynomial, 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 and so on, is it possible for me to have solutions that are in the form of polynomials or not? If we have this space of functions, we have exponentials, we have trigonometric, we have, I don't know, polynomials, power series, many different categories of functions. Between all of them, if we want to select a test case solution, to plug it and try to see if it is working or not, what is our best candidate? I'm asking you this question. Is it a good idea to have a polynomial as a solution guessed here or not? This is a polynomial, this is a polynomial, this is a polynomial. And if we take the derivative of polynomial first time and second time, then they are also going to be polynomials. So this whole thing be a polynomial equal to 0. So it seems a little bit reasonable. For instance, if I take e to the power of x, not a polynomial, I cannot say that a polynomial times e to the power of x plus another polynomial times e to the power of x plus another polynomial e to the power of x is going to be 0. Not in all of the cases. It is not general enough. So our guess is that solutions may appear as polynomials. But now I have two things that I need to answer. First and second questions is this. If I'm going to have a polynomial as my solution, what is the degree of the polynomial? Is it a second order polynomial, third order polynomial, nth order polynomial? What is the highest degree of this polynomial? They may at first guess that, okay, look for the degrees of these polynomials. For instance here, if this is of degree 2, if this is of degree 2, if this is of degree 7, maybe selecting a degree 7 polynomial is going to be super useful for us. But it is not the true case. These may be polynomials of lower degree, but the solution that we are going to get from here, from this assumption, may be a polynomial with higher degrees. So how can we deal with this? And second thing is that, even if we know the degree of the polynomial, what are the coefficients of the polynomial? Okay. As of now, I have no idea about this. I don't know about the coefficients. I don't know about the powers, the highest power of the polynomial. I also don't know if this is going to work or not. But I need to try, right? This is the mathematical endeavor. We need to try to some kind of find what is happening. What happens if I define my polynomial y in this form? Which is actually no more a polynomial, but a power series. That we show it, if you remember from calculus, we show it with this notation. A(n) x to the power of n. Okay? So our question reduces to this question. For a differential equation like this, what are the conditions such that we can find the power series solution? Okay? Next week we are going to talk about this, but maybe it is possible that you have forgotten some of the theorems and ideas about series, about the numerical series and functional series, especially that special type of functional series, which is this power series. For instance, about the radius of convergence of, or how can we find what is the radius of convergence of power series? Okay? Or for instance, is this a0 a separate function, a1x a separate function, a2x2, a3x3? These functions, when we are adding them together and when we are developing this series, and if we are taking this itself as a function, what kind of convergence do we have here? Is our convergence that we are talking here, is it point-wise convergence or uniform convergence? And if that happens, which for the case of power series it actually happens, can we take derivative of this whole thing term by term? Can we integrate this whole thing term by term? Because remember, you see, I have this y equal to this whole thing, right? How can I calculate the derivative of y, for instance? I will share a PDF file with you that summarizes all of these properties about power series. So for the next week, we can also be much more easier to work with them. But what you need to remember for now is that when we are taking derivative of power series, which means that when we are trying to take derivative of this function, we can take this derivative term by term, which means that we can have this a the power of n's derivative. I'm putting a huge question mark here because why it is possible to take this derivative one by one, term by term. This is the where that we need to talk about the uniform convergence of, and there is a lot of messy stuff here. But what is this going to be then? N from 0 up to infinity. Can you please take the derivative of this term? Yes, n x to the power of n minus 1. Again, this is itself a power series. So if we want to take its derivative, again we can take its derivative term by term and go on. We can also integrate a power series term by term, but as of now we do not need it, so don't worry about that. But these are the things that we have seen in calculus. Let me solve a few simple equations by this method and try to see if this really works or not. Example. If we have this y prime equal to y, okay? We have this differential equation. It's a first order differential equation. And we want to understand how can we use series in order to solve this differential equation. We already know the answer to this differential equation. That is why we are also trying to use this new method that we are trying to develop for the questions, for the differential equations that we know what are their answers, in order to check the validity of our procedure, and on the way, try to pick up the things that are necessary for this method to work, okay? Let's start with the assumption. If you are going to use this, solve this, by the assumption that there are a power series solution for this, what is our first assumption? Our assumption is that our y is a power series which are looking like this, okay? Why a power series? Because this is the zero polynomial, this is the polynomial 1, this is polynomial minus 1, okay, in that case. And we assume that maybe our answer is going to be in the term of a polynomial, but since I do not know the highest degree, and since I do not know the coefficients, I just assume that it is an infinite series like this, a power series. Let's take the derivative as we have done over there. What is our y prime then? N from 0 up to infinity of n, a n x to the power of n minus 1. Okay? We need to plug it into the equation, and after plugging it into the equation, we need to some kind of find the relation between these coefficients that we are having. Let me first write it in open terms, okay? What do I have for y prime? Y prime equal to y. Let me come here. Instead of y prime, what should I write? I need to write this, right? Instead of n, if you give 0, what do we get? 0, a0 something, which is 0. What if we gave 1? What do we have?
A1.
a1 x to the power of 0. What if n is equal to 2?
2a2x.
2a2x. What if it is 3?
3a3x.
3a3x, x squared plus the rest of this story, right? Maybe I can also, it's better to write one more time than continue. 4a4 x to the power of 3 plus the rest. No, instead of y, let's open y as well. If I give 0, what do I have?
A0.
a0. If instead of n we give 1, a1x, a2x, 2, a3x3 plus the rest. Okay? Now, look at these as some formal power series, which means that the x's are our placeholders for our coefficients. Which means that if these two are going to be equal, they're going to be equal if and only if the coefficients of the terms of x to the power of n, they must be equal to each other. Left hand side and right hand side, okay? What is the coefficient of x0? What is the coefficient of x0 in the left hand side?
A1.
A1. It is the term which appears without any x's. What is the coefficient of x to the power of 0, or the constant in the right hand, a0? Oh, we have already found something. What about coefficients of x to the power of 1? What is the coefficient of 2a2?
A1.
A1. From here, what can I say about A2? A2 is equal to A1 divided by 2, which is equal to A0 divided by 2. Okay? What about coefficients of x to the power of 2? What is the coefficient of x to the power of 2? 3a3 in the left hand side, and in the right hand side 8. Can you please from here calculate A3? It is A2 divided by 3, which is equal to what? Instead of A2, I can also write A0 divided by 2, right? A0 over 6, which I'm going to write as this 2, 3, 1. Okay? Let's write a few more terms. Oh, I should have let you to take a photo. Anyhow, doesn't matter. We have it on the record, so. What about coefficients of x3? What do we have here? 4a4 on the right hand side, a3. What is then a4 equal to? a3 divided by 4, which is going to be equal to what?
A0 over 4 factorial.
a0 over 4 factorial. And by n factorial, we mean n times n minus 1 factorial. It is defined recursively, which means that you need to have n minus 1, n minus 2 up to 1. You multiply all of these things. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, which is 2, 3 factorial is 3, 2, 1, 6. 4 factorial is 4 times 6. 5 factorial is 5 times 4 factorial, which is this 120, and the rest. Okay? Can you tell me what is an?
A0 divided by n factorial.
Yes. Actually, we have this as n minus 1 divided by n. Okay? And if you replace this in this is itself a recursive formula, right? It enables us to calculate the value of one higher n with respect to a lower one and some other coefficients or whatever. Okay? This is going to be a0 divided by n factorial. Okay? Now let's go back to our first assumption. We were looking for this kind of function, y, right? We were looking for this n, which seems that it is never going to be stopping in some place, so it is really an infinite series. And we were looking for the coefficients, and we did actually find them. So, with this assumption, what is our y? It is going to be a0 plus a1. a1 is again a0. Let me write this as 1 factorial plus, what do I have? Not to forget x here. Plus, what is my a2? My a2 is a0 divided by, this I can also write it as 2 factorial, because 2 factorial and 2 are the same thing. X to the power of 2 plus a3 x3, and what is our a3? a0 divided by 3 factorial. And what do I have here for the nth term? I have a0 divided by n factorial x to the power of n. Okay? Yes, x to the power of 3 plus 6. So look at this. This is a0 times 1 plus x to the power of 2 factorial, x to the power of 3 factorial, a0 n from 0 up to infinity of x to the power of n factorial. Is this something familiar to you? from your calculus courses. What is this?
Taylor series of e to the power of x.
Yes, this is the Taylor series expansion of e to the power of x, right? So I can write here this as a0 e to the power of x. Oh, interesting. Look at this. What was the solutions of this equation? It is a constant times e to the power of x, right? What did we get? Again, the same thing. But strangely enough, if we know that e to the power of x is a solution for that, this series, since we know the solutions are going to be unique, we must have this series equal to this as well. Here we know it, beforehand we know it. But in other cases, we may not be able to know it, right? So if we want to find a series expansion for a function, we just need to write a differential equation that has that function as its solution, then try to write this power series solution in place of it and try to figure out what's happening, okay? This is a side thing that we get on the way. But what is the first thing that we need to be careful about it? Yes, when we are writing power series like this, it seems that it is actually working. At least for first order differential equations. Let's make it a little bit more complicated, say. If we want to solve a second order differential equation, is it again going to work or not? For instance, if you have y double prime plus y equal to 0. If you have this differential equation, is power series method is going to be useful and is it going to work or not? How can we be sure about this? You still have time, good. Again, you know the solutions of this differential equation, right? This is the differential equation with constant coefficients. We have solved this equation many times. What are the solutions? Sine of x and cosine of x, right? So some kind of, we need to be recovering sine of x and cosine of x from this power series method. Let's see what happens. If we assume our solution is in this form, and our first derivative is like this is ending. What is our second derivative? Telefonlarınızı bırakırsak arkadaşlar çok sevinirim. Çok az kaldı, biraz takatli davranırsanız bunları bitirirsek çok iyi olur.
And science and minus.
Yes.
Minus
This is going to be this infinite series. N minus 1, a n x to the power of n minus 2. Okay? Let's replace it in the equation. If you replace it in the equation, what we are going to get? Y double prime plus y equal to 0. Then, n from 0 up to infinity of, what do I have? n minus 1, a n x to the power of n minus 2 plus n from 0 up to infinity of n a n x to the power of n equal to 0. No, just a n. Because I'm writing my functions, okay? The problem is that we need to collect the coefficients of x to the power of n together and put them equal to 0. But if you look at here, I have an x to the power of n minus 2 here and an x to the power of n here. So the powers are different from each other. So I need to some kind of convert this series by changing the indexing in such a way that the power of x here also becomes x to the power of n. And how can I do it? First of all, in numerical series, for instance, if I have, let's say 1 over n of n starting from 3 up to 5. If I want to extend this, not in the series form, but in the open form, what should I do? Instead of this dummy variable, I'm placing these numbers starting from this lower index up to this upper index and increasing it one by one. So it is going to be 1 over 3 plus 1 over 4 plus 1 over 5. If I want to change the indexes, not starting from 3, but maybe I want it to start from 1. Okay? What should I do? How can I change the form of this series in order to have exactly the same thing, but this time indexes is starting from different points.
You can call n minus 2 equals k.
Yes, you are shifting everything, right? You are calling n minus 2 equal to k, or look at this. So what is happening here? If we write this as n equal to starting, let's say it is starting from 1. So I'm taking 2 out of it. So it is a minus 2. I need to apply it here, 5 minus 2. So I will go from 1 up to 3. But here, instead of n, what did I do for these indexes? I made them minus 2, right? So I need to add this 2 here. So it is going to be n plus 2. Okay? Now, is it really the same thing? Let's check it. Instead of n, give 1. What will happen? 1 divided by 1 plus 2. Then n is equal to 2. If we give 2 here, it's going to be 1 divided by 2 plus 2. 1 over 4. And if n is equal to 3, so it is going to be 1 over 5. So this is exactly the same thing and it is working. Or generally, we can write this as if our n is starting from k and going up to L of an, this is equal to series of k minus m, L minus m, a of n plus n. This is called the change of index. You will use it here. How can I write this in such a way that the power of x here is x to the power of n? I need to do what? Add 2 to these indexes, right? So I need to shift them minus 2 here. So this is going to be n starting from minus 2 up to infinity sign minus 2. What is it again? Again infinity. What is this going to be?
N minus 2.
Not n minus 2. I'm taking a minus 2. So it is n plus 2, n plus 1, a, n plus 2, x to the power of n, plus series a n x to the power of n equal to 0. If n is equal to minus 2, what will happen to this? This is 0 times something, so it is 0. If n is equal to minus 1, what will happen? This will be 0, so the whole thing is going to be vanishing. So minus 2, for n equal to minus 2 and n equal to minus 1, we have this equal to 0, so we can get rid of it. So this can start actually from 0. Now look at this. Our indexes for series are the same. X to the power of n's are the same. So I can write this as n from 0 up to infinity of n plus 2, n plus 1, an plus 2, plus an, this whole thing, xn equal to 0. And when is this possible? we have power series such that it is equal to 0. This means that the coefficients must be 0, all of them. If instead of n you write 0, what do we have? Linear what?
We talk about like bildiğinin lise biz çekip hani sıfıra eşitlersek
Okay.
işte bunu lineer diyebiliriz o zaman ben işte.
We are not talking about change of coordinates or this kind of thing. We are just changing your indexes in order to bring everything together like this. Because I want to extract a recursive formula, like the example before, in order to be able to calculate what is happening, step by step. That is why we are doing this kind of things. And if I have this power series equal to 0, it means that all of the coefficients of this power series is equal to 0. So the coefficient of x to the power of 0 is 0. Coefficient of x to the power of 1 is 0. X to the power of 2 is 0. And generally, all of the coefficients of x to the power of n are equal to 0. So I can say that for n greater than or equal to 0, what I have n plus 2, n plus 1, a n plus 2 plus a n, this is equal to 0. So what do I have? I have a of n plus 2 equal to minus a n, n plus 2, n plus 1. Okay, this is my recursive formula. These recursive formulas are actually being used when we are trying to find it, okay, when I'm writing a series like this, is this series really have a convergent region? Is it really valid? Is it defined or not? That is used for this kind of things, but we will not get into that parts of the story in this course, so don't worry about it. What will happen here now? If my n is equal to 0, what will I have? I will have a2 equal to what? Minus a0, 2 factorial. What if n is equal to 1? I have a3, which is going to be equal to what? Minus a1 divided by 3 times 2. Okay. What if n is equal to 2? I'm having a4, right? And what is my a4?
Minus a2.
Minus a2 divided by what?
4 times.
4 times 3. But a2, I know what it is. I have no idea about a0 and a1. They can be anything. But a2 I know. And what is it? Minus a0 divided by 2 factorial. So I can write this as this minus and minus cancel. a0, I have 4, 3, 2, 1. Okay? So let me come write it here. a4 is going to be equal to a0 divided by 4 factorial. What if n is equal to 3, which will give me a5? What is going to be a5? It is going to be, again, we are using this recursive formula, right? If I place n equal to 3, I have my a5 here, so it is minus a3 divided by 5 times 4. Can I write this in lower terms?
Yes.
What is my A3? It is minus A1 divided by 3, 2. So it is going to be minus with minus cancelling. A1 divided by 5 factorial. Let's go one more. What is our A6 equal to? As we know, it must be equal to minus A4 divided by what? 6 times 5. Which is going to be equal to what? You know what is our A4 is. So, minus A0 divided by 6, 5, 4, 3, 2. So it's 6 factorial. What about A7? A7 is going to be minus A5 divided by 7 times 6, which is going to be equal to minus A1
Or
7 factorial. Yes. Okay. This much is enough. And by the way, in the final exam, if you are not able to write this general recursive formula, okay, in order to find out what is happening, if you like the example before, write it up explicitly and find first 4 or 5 terms. It is also fine for me. Okay? So, what I need to do, my general solution, my y, was what? A0 plus A1x plus A2x2 plus, let me write this in blue. Change of color would be good. I'm having this A0 plus A1x plus A2x2 plus A3x3 plus the rest, right? Let's replace them. Some of the terms that are even, they are all written in terms of A0, right? And the odd terms are written in terms of A1. So, I'm collecting even powers to one side, to one bracket, and odd powers to another bracket. So, I'm just going to write this as equal to, or in here, equal to. A0, I keep it. I have A1x, let me write A1x here. I have A2x2. Instead of A2, what I'm going to write?
minus A0.
Minus A0 divided by 2 factorial. X to the power of 2. Plus A3x3. What is A3? Minus A1. So I'm writing it in minus A1, 3 factorial, x to the power of 3. I have x4, right? A4, x4. What is A4? A0 divided by 4 factorial, x to the power of 4. I have A5, x5. What is A5? A1 divided by 5 factorial, x to the power of 5. I have A6, x6. What is A6? Minus A0 divided by 6 factorial, x to the power of 6 plus the rest. And from here I have the 7 that I'm just letting it go. Can I write this now as A0 times 1 minus x to the power of 2 factorial plus x to the power of 4 factorial minus x to the power of 6 factorial plus A1 times what? X minus x3 divided by 3 factorial plus x5 5 factorial minus x7 7 factorial and the rest. Can I write this in this form? Are these two familiar to you or not from calculus? They are the Taylor expansion of this. This is cosine of x, and this is sine of x. So we have a constant times cosine of x plus another constant times sine of x. What was the general solution of this differential equation? Y double prime plus y equal to 0. It was c0 cosine of x plus c1 sine of x, right? So we have exactly the same result. So actually it is working for us. Now, of course, these are very simple equations that we can solve them. What about the situation is not that simple? For this, we will have examples for the next lecture. Okay? By the way, I will upload a file for you to review these cases about, I don't know, power series, analytic functions, and this kind of things. Also, I'm just going to give this very well-known equations, like Lejean's equation, Bessel's equation, or Hermite equation, or this kind of Chebyshev equation, this kind of equations, as homework exercises for you. So maybe I'm just going to solve one or two of them, because next week we need to talk about some of the special properties of these functions, and also talk about series solutions in general. We need to talk about the regular points, irregular points, a few stuff. We may not have time to deal with a lot of this kind of special functions, but yeah, as homework exercises, you are free to do them, and it will be most likely like that. Anyhow, I will continue next week. Do you have any questions that you would like to ask? Are you fine? You can take the picture of the board if you want, and Allah'a emanet olun.